In this video, we're going to be talking about one-sided limits and the difference between one-sided limits and two-sided limits. So the standard limits that you see with just as a limit of x approaching, I don't know, 0, right, of some function. This is a two-sided limit. So what is a two-sided limit? Let's draw it out. Say you have a graph, some random curve, doesn't matter what the graph is, and you want to solve the limit as x approaches 0. Well, as x approaches 0, there's a dot. So, right, this is the point on the graph as the limit of the function as x approaches 0. Right, this is x of 0 along the y-axis. And with the two-sided limit, you measure the behavior of two dots as they approach the blue dot infinitesimally close on both sides. This is what a standard two-sided limit does. Two dots on either side of whatever point you're trying to find the limit of, and you drag this green point super close to the blue point, and you measure the behavior of the green point as it gets close to the blue point. And the reason why I specify behavior is because sometimes your function doesn't have a value at certain points, like in the cases of holes. Right? A hole literally just looks like a circle on the graph. But you can still find the limit of the hole using two-sided limits. You can also find the limit of a hole using one-sided limits. So let's talk about one-sided limits. What's the notation for one-sided limits? Well, the notation for one-sided limits is x approaches the positive side and as x approaches the negative side. There's two notations. You're going to see a plus on your exponent or superscript, if you use Google Docs, superscript notation. But let's draw a random curve again. All right. Say the curve looks like this. And you're trying to find the limit as x approaches 0 from the positive side. So let's say that this point is at the origin. All right. Now, in a two-sided limit, you had two green points approaching from both sides, and you measure the values of those points, the y values of these green points, as they approach the function values of those points as they approach the blue point right here. Now, for a one-sided limit, instead of measuring the behavior of 2 points on both sides, you measure behavior of just 1 point on one side. So you get really close on the negative side. So this right here is actually the negative one. And for the positive limit, you get really close. Let's pick the right color. You get really close from the right side. So this right here is the positive. Let's use a different color. This right here is the positive limit approach. So what's the difference? Well, the positive limit approach from the positive side. Now keep in mind, you don't need to approach from the limit 0. It might be a little confusing, but let's say you want to approach from this limit right here. So the limit as x approaches, let's say this looks like 5. X approaches 5 on the positive side. Well, the positive side is just from the right. So as the limit approaches from the right, infinitesimally close to your x equals 5 point, and measures the behavior of this green point as it approaches infinitesimally close. See, the reason why I specify that is because since I put the point at the origin here, you might think that it only comes from the positive. You can only find one-sided limits from the positive half and the negative half. No, the negative and the positive just represent direction. So the positive notation right here just represents that you come from the right side, and the point on the right side infinitesimally approaches the x value of your function from the right, scooting to the left. And a limit approaching from the negative side, so a limit as x approaches, let's say 4 minus. Let's say this looks enough like 4. So not negative 4, but 4 from the negative side. You have a point on the negative side, the left side usually. Not the left side usually, left side literally all the time. In standard convention for Calculus 1 graphing, limits will approach the negative side from the left. So you have a point on the left of this 4 point, and you infinitesimally drag. not infinitesimally, but you drag the green point infinitesimally close to the blue point. So super, super, super close, just from the left side, not from the right, not from the above, not from below, literally just from the left. And the reason why this is important is because you're not going to get good-looking graphs like this all the time. You're going to get graphs that are discontinuous. And discontinuous graphs, well, in some places, a limit doesn't even exist in discontinuous graphs. So one-sided limits can, but one-sided limits can't exist. So let's say this is at -2. All right, x equals -2. What if we find the limit as x approaches to -2 from the negative side of our function? Well, let's specify our y values first. This is a y value of 3. Let's say this is a y value of 1. Or a function value of 3 and a function value of 1. Well, if we take the limit of at -2, this discontinuous part of the function, from the negative direction, so negative direction, the left side, let's draw a point on the function from the left side of -2. You drag the point infinitesimally close to -2, x equals -2, and then you get a value of 3. Right? That is the function value when you get infinitesimally close to -2 from the left side. But what if you measure the one-sided limit from the right side? So as x approaches -2 from the positive side. Well, look what happens. If we draw some point on the right side, doesn't matter how far we draw the point, I'm just drawing them like this distance approximately. You could start the point in it like really, really close if you want it as well, but I'll just start it further away just for visualization's sake. And you drag it infinitesimally close from the right to the left. If you drag it super, super, super close at -2, you're still staying on this line, this y equals 1 line. So what would the value of our one-sided limit from the right be? Well, your value from the one-sided limit at -2 from the right would be 1. The reason why it will be 1 is because you're approaching from the right. So if you approach this function from the right, you're not going to instantaneously skip up here and then get some value of 3. No, you're going to get a value of 1. And that is the behavior as this limit infinitesimally approaches this non-filled point here. So you can consider this kind of like a whole. But remember, limits measure behavior, not the actual value of the function. If you plugged in f of -2, if you plug in -2 as the x value for this function, you would get 3. And the reason why is because 3 is where the filled point is here at -2. And the reason why, and maybe if you guys, maybe if I'm being more clear, the reason why I didn't fill this point here is because you can't have two, fails the vertical line test, right? You can't have 2 points, you can't have 2 y values at the same x value. So that means I have to make this, leave this part unfilled and this part filled at the top. And a quick side note, if you don't know what continuity is, I have a video on that. Link will be down in the description if you're curious. But if the two one-sided limits do not equal each other, so if these do not equal to each other, so equal sign slash, so this means not equal, then the limit as x approaches -2, just the standard two-sided limit for the function does not exist. The function does not exist at -2 if the one-sided limits don't equal each other. That's just one of the conditions for a two-sided limit to exist. Now, here's another curious thing of a one-sided limit. And it refers to, and I'm referring to when you have a vertical asymptote or a horizontal asymptote. Actually, a horizontal asymptote, you could use a two-sided limit. But that's a different video. Infinite limits is a different video. So what I mean by infinite limits is as the limit approaches -infinity or positive infinity, right? -infinity or positive infinity. This measures horizontal asymptotal behavior. But let's talk about one-sided limits. All right. Let's say you have a vertical asymptote at x equals 0. Let's say our function is 1 over x. Right? This looks like a standard 1 over x function. Hopefully you know what that looks like. Let's say you want to approach this function limit as x0 approaches from the negative side of your function 1 over x, right? So the function 1 over x is drawn here. This is the y-axis, this is the x-axis. And we want to approach 0 from the negative side. Well, we have a vertical asymptote. So let's draw with the dotted line. We have a vertical asymptote at x equals 0. So at x equals 0, your function shoots up and blows up to infinity. And the reason why is because you can have an infinite amount of numbers between 0 and 1. So you just keep putting down numbers, and this chart just keeps going higher and higher and higher and higher and higher. So how do you measure behavior of something using a limit with a vertical asymptote? Well, if you approach from the negative direction, as always, draw some dot. Doesn't matter where you draw the dot on the graph, as long as it's on a continuous part of the graph. And you drag this dot up, 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 all right, closer and closer to 0 from the negative direction. So always negative directions, always from the left. And you keep dragging it up, but wait, it just keeps going. As the limit keeps going up and higher, it just blows up to infinity. You can't, the dot just keeps going closer and closer and closer and up higher and higher and higher to 0. So it gets closer and closer to 0, but higher and higher up and blows up to infinity. So in a technical sense, this limit does not exist because you cannot equal infinity. But some teachers will have you write down both does not exist and positive infinity. So this thing goes up to positive infinity because you're going upwards. So if you go upwards, positive infinity, right? But let's write the limit as you approach 0 from the positive direction. So from the right. What does this equal? Well, let's draw the dot somewhere on the right of the graph and then drag this dot close to 0, right? But remember, this is a vertical asymptote. So as it gets closer and closer to 0 from the positive direction or from the right, maybe I should use a different color for this. Let's underline this with blue and let's underline this with green so you can differentiate the dots. And as this blue dot gets closer and closer to 0, oh, look what happens. You go lower and lower and lower, but you don't stop. This vertical asymptote is infinite. It keeps going and going and going. So your limit does not exist. But the limit also approaches negative infinity. And it's negative, keep in mind. You need to take the difference between the positive and the negative infinity. There's a difference between them. Positive infinity goes upwards, negative infinity goes downward. So in this case of a vertical asymptote, when you approach from the right, you get negative infinity. But sometimes if you approach from the right, so sometimes you have a limit that approaches, I don't know, maybe there's a vertical asymptote at 2 and you approach from the right, you'll get positive infinity. So don't always think that a limit from the right equals negative infinity. Don't always think that a limit from the left or the negative direction equals a positive infinity. So for this problem, we're going to do some true or false just to get a grasp of some concepts behind limits and one-sided limits. So let's start off with the first one. So the limit as x approaches 10 for this function is equal to 0. Well, does that make sense? What do you guys think? So the limit as x approaches this point right here. Well, it is, in fact, true. So good check. And the reason why is because when this function approaches 10, you approach a y value or function value of 0, since this point is on the x-axis. So if the point is on the x-axis, the function value or the y value is equal to 0. So this is good. This is true. How about when as the limit of x approaches negative 2 from the positive side equals 3? So let's go ahead and look at negative 2. Well, negative 2, oh, it's discontinuous here. So one-sided limit works pretty well. But let's go ahead and draw a dot here. A dot on the right side. Let's draw a dot right here, actually. And from the right side, you drag the dot infinitesimally close to negative 2. So do you get a value of 3? Well, we don't. And I don't even know, I think this might be asymptotal. Like, it doesn't even end here. It doesn't have like a circle at the end, just like these do. So this might be asymptotal. It might blow up to positive infinity. But for sure, as the limit approaches negative 2 from the positive side, you don't get to 3. right? 3 is right here. Oh, ooh, I'm using white on a white background. 3 is white right here. It's literally right here. This green dot goes on to who knows how high. So this right here is false. All right. How about for the limit of x approaches negative 8 equals the function value of negative 8? Well, let's look at negative 8. Negative 8 is right here. And is this true? Well, as the limit of x approaches negative 8 for our function, we get infinitesimally close on both sides to this hole here. So as the function approaches negative 8, right, we actually get negative 6. Correct? This is kind of looks like what the filled in hole is. But what happens if we just plug in the function value for 8? So if we plug in the function value for negative 8, well, we would get this dot here, this point here. Since this point is actually part of the function, it's going to give you a value of negative 3. Negative 3 is the y value for this function. Ooh, let's fix the arrow. Negative 3 is the y value, or the function value, at negative 8. But the limit equals negative 6. Since limits, when there's holes, the limits kind of ignore the holes. It just pretends like the function was continuous from the first place. So this right here is not true, because the function value is negative 3 and the limit value is negative 6. So these two are not equal to each other. Okay, what about as the limit approaches 6 is equal to 5? Well, let's look at 6. 6 is right here. And as the limit from both sides, this is a two-sided limit, there's no negative symbol or positive symbol, approaches negative 6. Let's draw 2 dots on either side, and let's draw an arrow, kind of infinitesimally approaching closer and closer. And both of the values of these points right here for this two-sided limit are different. This value is, or the right-sided limit has a value of, why is there a dot up here? The right-sided limit has a value of 5, right? A y value of 5. But the left-sided limit, or the negative limit, has a value of 2. So since these one-sided limits do not equal to each other, this should be d-any. Therefore, the limit does not exist, so it can't equal 5. Well, now we actually solve for one-sided limits. So sometimes for one-sided limits, you're going to get piecewise functions, which I will show you. I have a video on that, how to solve for limits with piecewise functions. But for now, with one-sided limits, we're going to use a crutch, we're going to use a picture. Okay, so these pictures are going to help you a lot when solving for one-sided limits, but make sure you know how to draw graphs. That's very important for solving limits, because if you don't know how to draw graphs, it will make some things 10 times harder. But let's go ahead and use this picture to solve for the one-sided limits, just to understand the concept and how to solve one-sided limits. That's the main goal of this video. So the limit as x approaches negative 2 from the negative direction. So as x approaches negative 2, which is right here, from the negative direction, so from the left, you get a red dot. Let's draw this, get really, really, really close to negative 2. X equals negative 2 from the left. Well, what value, y value do you get? Or function value? Well, the behavior of this dot that's approaching from the left, this red dot, that's approaching from the left and getting to the function point, is equal to 0. Since this red point kind of gets super close to 0, or a y value of 0 here. Okay, how about for a limit as x approaches negative 2? So the same negative 2 point, expressed by this arrow, from the positive direction. So from the positive direction, it comes from the right. So let's draw this dot out, and then drag this dot super close to x equals negative 2. Well, what you actually get is a limit that approaches 2. Since the y value as this dot gets super close to this kind of discontinuous strip of the function, you get a y value of 2. Alright, but now that we have your both one-sided limits, does the regular limit exist? It does not exist, because they aren't equal to each other. 2 is not equal to 0, no matter what the flat earthers say, but 2 is not equal to 0. Don't I don't even know why I don't even know why I'm making so much time out the video to say that. Okay, I'll just keep moving on. Limit as x approaches 2 from the negative direction. So as x approaches 2 right here from the negative direction. Negative, hence the left. What am I doing drawing it on the right? So as this green dot gets dragged super close to x equals 2, what is the behavior of the function? Well, you get a y value of negative 2. So negative 2 is the answer. Alright. How about for x approaches 2 from the positive direction? Well, from the right, this time, you drag super close to the x value of 2. Well, what y value do you get? You get a y value of 2. Okay, I'm drawing with green again. I mean white again on a white background. Y value of 2. So this is 2. So does the limit exist? Negative 2 does not equal 2. Limit does not exist. So, as always, I need to mention OpenStax. It's a free online textbook. Link will be down in the description. I get my problems off there. So I got my problems in this video off of there, so I have to include this. But if you found this video helpful, consider subscribing and liking the video. Thanks for watching.